Okay, so this is lecture 27, and before we start a discussion on compact metric spaces, we will see a nice application of what we have seen so far. So today we will prove a very interesting theorem. So SON is connected. In fact, SON is also path connected, but that takes a little bit more work. And so in this course, we will prove that SON is connected. Before we start the proof, it is perhaps worth appreciating that the definition of SON is somewhat complicated. So recall that SON is all those matrices A in M and R such that A transpose A is equal to identity and determinant of A is 1. So to show that, if you were to try and show directly that SON is path connected, then it would probably be quite hard. Yeah. So let's begin the proof. So first consider this map from SON to the sphere Sn minus 1. Okay. Before that, so let E1 in Rn denote the column vector (1, 0, 0). Okay, and consider the map from SON to the n minus 1 sphere given by we take a matrix A. So let's say n is greater than or equal to 2. So we take a matrix A and it gets mapped to AE1, right? So we are taking this matrix A in SON, and this is getting sent to the first column. Right. So a priori it's not clear that the image lands in Sn minus 1, but let's just check that. So AE1, so we need to like a priori this is a map from SON to Rn, and we need to check the image lands in Sn minus 1, right. So SON has the subspace topology from M and R, and this is just a projection on some coordinates, right. So therefore this map is continuous. So this map is continuous, right. So let's compute the norm of this AE1. The inner product of AE1 comma AE1, this is equal to, so this is the standard inner product on Rn given by V comma W is defined to be W transpose times V, right. So when we use this, so we get this inner product is equal to A times E1 transpose times AE1, which is equal to E1 transpose A transpose A E1. But now A is in SON, which means A transpose A is identity, so this is equal to E1 transpose E1, which is just equal to 1, right. So this implies that the image lands in Sn minus 1. The norm of this vector AE1, that is 1, right? So we have this SON, we have this continuous map to Rn, and the image actually lands inside Sn minus 1. And since Sn minus 1 has a subspace topology from Rn, this implies that this map we have defined, SON to Sn minus 1, is continuous. Okay. Next, let us consider the subgroup H equal to SON minus 1 sitting inside SON as follows: 1, 0s here, 0s here, and here we have this matrix SON minus 1. Okay. So we claim that AE1 is equal to BE1. So if we call this map phi, so what we are saying is phi of A is equal to phi of B if and only if B inverse of A is in H. Okay. So let's check this. So if B inverse of A is in H, right? So this implies that B inverse of A is equal to H for some H in H. This implies that A is equal to B times H simply by multiplying on the left with B. So now we apply both these on E1. So this will imply that AE1 is equal to B times HE1. Yeah. But now note that HE1 is simply equal to E1, right? Because when we apply this, a matrix of this type on E1, we get back E1. Right? So this implies AE1 is equal to BE1. Okay. So now let's prove the converse. Conversely, suppose AE1 is equal to BE1, then multiplying with B inverse on both sides, then this implies that B inverse A applied on E1 is equal to E1. Okay. So we let C be the matrix B inverse A. Right. So then CE1 is equal to E1. Right. So this implies that C is a matrix which looks like this. So CE1 is equal to E1, which means the first column looks like this and the others can be anything. Right. Now as A and B are in SON, this implies B inverse A is equal to C is also in SON, right? And from the condition C transpose C is equal to identity, so if we write C as columns C1, C2 up to Cn, right? So this C transpose C is equal to identity, so this becomes C1 transpose, C2 transpose, Cn transpose into this column C1, C2 up to Cn is equal to identity. So this implies Ci transpose Cj is equal to 0 for I not equal to j. Right. So if we now, but this Ci transpose Cj, that's just the inner product Ci. Yeah. So this implies that the inner product Cj comma C1 is equal to 0 for j not equal to 1, right. But C1 is this column vector 1 0 0, right, and Cj, so C1 is this column, and let's take C2, C2 will be this column. So when we take the inner product of C1 and C2, we get this entry, this first entry over here, right. So since the inner product is 0, this implies that this entry will be 0, and similarly this entry will be 0, and similarly all these entries will be 0, right. So as C1 is this, from this we conclude that C is this matrix, looks like this. And here we have whatever, right. So this implies that C belongs to H. Okay, so thus B inverse A belongs to H, which is what we want to prove. Okay. Next we claim that the map SON to Sn minus 1 is surjective. Okay. So recall that given a vector V with norm V is equal to 1, so V is in Rn, right, we may extend it to an orthonormal basis V is equal to V1, V2 up to Vn of Rn, right. And so now let A be equal to the matrix V1. We write these vectors as column vectors and we let this matrix A. So A is an n cross n matrix, right. So then clearly, so this matrix A transpose A is going to be equal to this matrix obtained by Vi, taking the inner products of Vi and Vj. There is an easy check, right, and this is clearly equal to identity because the Vi's, they form an orthonormal basis, right. So if determinant of A is equal to minus 1, then we simply replace the last column by negative of that, then let A prime be the matrix V1, V2 up to minus Vn, right. So then we easily check that A prime transpose A is equal to identity and determinant of A prime is equal to 1, right. So moreover, the first column of A prime is V1 is equal to V is equal to V, right. So this proves that. So this is the map phi. This proves that phi is surjective. Okay. And we need one more ingredient. So let's look at that. So if A is in SON, then consider the map from SON to SON. This is given by left translation by elements of A. So precisely this map is, it sends a matrix B in SON to A times B. Yeah. So it's easily checked that if A and B are in SON, then obviously A times B is in SON. In fact, SON is a subgroup of GL and R. So let's check that this map is continuous. So to show this map is continuous, so note that SON has a subspace topology from M and R. So it's enough to check that this LA, after we compose with this inclusion, right? So this composite is continuous, right? But this composite map, this dotted arrow, it factors like this, MNR to LA, right? So both these triangles commute. We can take this matrix A is fixed, and we can define left multiplication by A on MNR itself, yeah? So here also it's A goes to AB, right? But clearly this map is continuous because all the coordinates, they are just some linear combinations of the coordinates of AB are simply linear combinations of the coordinates of B. So therefore, this horizontal map is continuous. As a result, when we look at this map, that is continuous because we have just restricted this continuous map to SON, which means the dotted arrow is continuous, which means the map LA which we started with, that is continuous, right. So similarly, LA inverse, so let me just write, yeah. So let's call this map A, B, C. LA, let's call this LA tilde. Yeah, so to show LA is continuous, enough to show B compose LA is continuous, right? But B compose, it's enough to show B compose LA is continuous because SON has a subspace topology from MNR, right? But B compose LA is equal to this dotted arrow A, which is equal to LA tilde compose C, right? And LA tilde is continuous because LA tilde, it's enough to check what the coordinate functions of LA tilde are continuous, and so, and C is just a restriction of LA tilde to SON. This implies LA tilde compose C is continuous. Yeah. So this implies LA is continuous. Okay. So similarly, LA inverse is continuous. But clearly we have LA compose LA inverse is equal to identity, which is also equal to LA inverse compose LA, right. So thus, so we have LA is continuous and LA is a bijective continuous map, and its inverse, it's clear, is L of A inverse, and that is also continuous, yeah. So thus LA is a homeomorphism. Okay, so now with these ingredients, we are ready to prove that SON is connected. So we will prove the theorem by induction on M. So the base case is n equal to 1, right. So in this case, SO1 is simply, there's just one element which is obviously connected. Right. So assume we have proved that n is greater than or equal to 2, and we have proved that SOK is connected for, okay, so sorry. So let's assume that n is greater than or equal to 1 for k lying between 1 and n. Okay, so now we will show that SON plus 1 is connected. So consider the map. SON plus 1 to Sn, right? So note that as n is greater than or equal to 1, we have n plus 1 is greater than or equal to 2. So therefore, we can consider this map which we analyzed before. So if SON plus 1 is disconnected, then we can write it as the disjoint union of two non-empty disjoint non-empty open sets and so also closed. Right. So let's pick any element of SON plus 1, right, and let H be the subgroup SON contained inside SON plus 1, right. So so A is in SON plus 1, so A is either in U or it's in V. So assume that A belongs to U, right. So then we can take this subset AH and we can write it as AH intersected U disjoint union AH intersected V, right. Yeah. So as LA, so LA is from SON plus 1 to SON plus 1 is a homeomorphism, right, and we have H sitting over here, LA sends it to AH sitting over here, right. So LA is a homeomorphism, so therefore it's a homeomorphism. This implies that LA restricted to H, this map from AH to AH, is also a homeomorphism. Right. So and as H is connected, so H is homeomorphic to SON, and we are assuming by induction that SON is connected. So as H is connected and AH is homeomorphic to H, this implies that AH is also connected, right. So thus one of these two open sets has to be empty, but A belongs to this set, so this implies that this set over here has to be empty, or in other words AH is completely contained inside U, right. So we have proved that if A belongs to U, then AH is completely contained inside U, right. Similarly, if B belongs to V, then BH is completely contained inside. Okay. So now let's consider this map from SON plus 1 to Sn, right. So U is closed and SON plus 1 is compact, implies U is compact, right, which implies phi of U is compact in Sn. yeah, which implies that phi of u is closed, right? So similarly, phi of v is also closed, right? So as P is surjective, this implies Sn is equal to P of u union P of v. So we claim that this union is disjoint. Is disjoint. Right? If not, there exists some vector v in P of u intersection P of v. Right? So this implies that there exists A in u and B in v such that phi of A is equal to A E1 is equal to V is equal to B E1 is equal to phi of B. Right? But now we know that this happens, this will imply that B inverse A belongs to H, which implies that A belongs to B of H, and since B belongs to V, B of H is contained in U, contained in V, right? So which is a contradiction, because we assume that A is in U and U and V are disjoint. Yeah. So thus we have written, if SON plus 1 is disconnected, then Sn is going to be P of U disjoint union P of V. Right? We can write it as a disjoint union of non-empty closed subsets, which means it will also be the disjoint union of non-empty open subsets, which means Sn will be disconnected. Yeah? But this contradicts, but we have seen before that Sn is connected. The fact that Sn is connected. Yeah. So thus SON plus 1 is connected. So this completes the proof of the theorem. So we will end here.